to another video. Now in this video we're going to be looking at projectile motion again, but with a special emphasis on the time of flight. Now I'm going to tell you what the time of flight is. I'm going to describe everything you have to know about the time of flight so that you can tackle questions related to it when you find them in the exam, when you come across them in the exam. So let's get into it. Okay, so I'm going to write on top here, time of flight. Okay, so this is the time of flight of what? This is the time of flight of a projectile. Remember in the previous video we mentioned what a projectile is. We said a projectile is the object that is launched or projected or ejected from a certain point that follows a certain path that we called the trajectory. So the time of flight, or the statement the time of flight, is referring to the time the projectile takes in order to complete its journey. What we would call, say, the full cycle of the projectile. Basically it will be something like a parabola, something like this. So the time of flight is the time the projectile, that is the time that object which has been launched, takes to move from this point A up to this point B. Now the projectile need not to follow this exact path. You can be asked to find the time of flight for a projectile that has been launched from this point and takes this path in the air, calling this A and calling this point B. You may be asked to find the time of flight associated with this path, that is from point A to point B. So basically in this case, just like in this case, our object travels from this point A up to this point B. The time it takes to move from point A to point B is what we are calling the time of flight. So again, when we come to this path, the time the object takes to move from this point A up to this point B again is called the time of flight. And again, this applies, say, our object has been launched from this point A and it follows this path, and say there is a cliff on top. It's basically the opposite of this. Instead of launching our projectile from the cliff, this is a cliff, now we're launching our projectile from the ground and it hits the cliff. This is now our point B. Again, you might be asked to find the time of flight associated with this trajectory, associated with this path, or associated with this motion. It all differs. So you have to understand what the time of flight is. Don't try to memorize it, or don't try to memorize the formulas associated with certain trajectories, like memorizing how exactly you find the time of flight in this scenario. In this scenario, it won't work. You have to understand exactly what we mean by time of flight and how we compute it in different situations. So let's get into that exactly. We're going to begin with this path, which I believe is the simplest path, and then we're going to attack this path and this path, or any other kind of path you might think of. Okay, so the first case we're going to be dealing with is associated with this path, where our object is projected from this point A, say at an angle theta with a velocity v. This is the first case we're going to be looking at, where we've got a very nice path which hasn't been broken into parts. Now, the first thing that is to always come into mind, the first thing that is to be drilled into your mind every time you want to calculate anything related to projectile motion is this. Projectile motion is broken down into component parts. The way we deal with projectile motion calculations is by decomposing or breaking the motion into two components. And what's that? That is the vertical aspect of the motion and the horizontal aspect of the motion. What do we mean? When our object is projected from this point A and moves following this path B, remember it has been projected with a velocity v, and we mentioned in our previous video that when we're dealing with calculations associated with this velocity, we do not take it in its raw form. We break it down into components. A component associated with the vertical and a component associated with the horizontal. That's exactly what I'm talking about here. We deal with the vertical aspect and we deal with the horizontal aspect. Now, the horizontal aspect of the projectile's motion is the easiest to deal with when it comes to time of flight. Why is this? Now, what happens is when our object is projected, and this applies in any case, when our object is projected from a certain point, the horizontal component of the velocity, which in this case is v cos theta, let's first find the components of this velocity. Which velocity again are we talking about? This is the velocity of the launch, the velocity at which our projectile has been projected or launched at. Now, let's first find our velocity. Now, the vertical component, if you remember, I'm going to be using the shortcut we mentioned in the previous video. The velocity in this case would be v sine theta. So, let's call this vy, the velocity associated with the vertical component. The velocity in this case would be v sine theta, and the velocity associated with the horizontal component would be what? Let's call it vx. In this case, it would be v cos theta. Now remember, theta is just representing an angle. If you're given an angle of say 35 degrees, 75 degrees, 40 degrees, 20 degrees, that's what you substitute for theta. And if you're given the magnitude of this velocity, keep that in mind, the magnitude of this velocity, that's what you substitute in for v over here. Now, I could do this, but I don't want to confuse you, so I'm just going to use a simple notation. The only reason I mention that is for other people who might be like, okay, you're abusing notation. I'm not. Now, our horizontal component for this velocity is vx. That is the horizontal. Then the vertical is associated or as the velocity vy over here. Now, these are just magnitudes. Now, for the horizontal aspect of the motion, remember I told you that when it comes to calculating the time of flight, that is the time the object took to move from point A in this way up to point B. It's much easier to deal with when you're using the horizontal aspect of the motion. Now, what exactly do we know about the horizontal motion? Now, always bear this in mind. This applies every single time. The horizontal motion is completely different from the vertical motion in the sense that the horizontal motion is not associated with any acceleration. And because it's not associated with any acceleration, that is, the acceleration is zero, we can simply use the normal speed formula, or the usual speed formula, if you will, which is speed is equal to distance over what? Over time. So if you want to find the time of flight of this object, all we have to do in this case, when we're using the horizontal aspect of the motion, all we have to do is substitute the speed, that is vx, and the distance, d. This is the distance. We call this distance the range of the motion. We're going to be dealing with that in another video. I'm just going to put it in brackets so that you start reading it into your head. The range. So all you need In this particular scenario, when you are using the easiest formula or the easiest method, all you have to possess is the speed and the distance. Now, what is the speed? The speed is, let's do this. The speed is Vx or V cos theta. Let's write V cos theta. In this case, it's V cos theta. Please do not memorize this. Do not say, okay, so Vy is equals to V sine theta and Vx is equals to V cos theta. Why do I say that? The moment your theta is put in this position, like if you come across a question where theta isn't below this arrow but lies on the other side of the arrow, say here, and you're not given an angle here, everything changes. This becomes a cos and this becomes a sine. If you want to understand how exactly do you determine where sine goes and where cos goes, watch my previous video where I talk about velocity, the first video on projectile motion. So please, do not memorize this. Understand where they are coming from so that you yourself too can derive these formulas. Now, so in this case, we have the speed is equal to V cos theta. Now, what is the distance? The distance is the range. And what are we looking for? We are looking for the time. So once you have your speed or your horizontal component of this velocity, which by the way doesn't change. Why? Because we have got zero acceleration. Acceleration is the rate of change of the velocity with time. Now, in this case, the velocity doesn't change because we've got zero acceleration in this horizontal direction. So it remains constant throughout the entire journey. Again, this is the horizontal component. But when you come to the vertical component, because we've got the acceleration of gravity acting in the vertical aspect of the motion, the velocity is going to be changed. It's going to be varying throughout. We can, in a way, actually write this as Vy as a function of time. Why? Because it's going to be varying throughout. But because I don't want to confuse a lot of people, I don't want you to try to drill a lot of information in your head at once. Just put this in your head. So this is constant throughout the entire journey. So say our object is launched from point A. When it gets to this point, it has a certain vertical component of the velocity and it has another component of the velocity. And when it gets to this point, it has a certain component of the vertical velocity and a certain component of the horizontal velocity. And when it gets here to the final point B, again, it has a certain, the arrow is actually facing down here. The same applies in this case. So it has a certain component of the vertical velocity and a certain component of the horizontal. So what am I saying when I'm saying this is constant? The horizontal component of the velocity is constant, which is to our advantage. What I'm saying is, at this point, remember when the motion begins here, this V cos theta, this has a certain value. What I'm saying is, when I say it remains constant, is at this point, this arrow, which is associated with this horizontal component of the velocity, this velocity is still the same. It's the same as what was exactly here. And when you get to this point, notice what begins to change is the vertical component of the motion. Previously, it was facing up and it was getting smaller and smaller and smaller. Now it's getting bigger and bigger, but it has changed the direction. But this doesn't change. This is always the same. What is this? The horizontal component of the velocity. It doesn't change. So hence why I'm saying this is a constant. Because of that, you simply use the speed is equals to distance over t formula, because this formula is not associated with any acceleration. So t, in this case, we're moving from A to B. T, the value for t you get is the time of flight associated with this motion, despite the fact that the object traced this funny looking path, you can simply treat it as if it traced a linear path using this horizontal component of the velocity. So this is one way of getting the time of flight. We're going to be looking at a bunch of examples in the future, but for now I want you to understand the ideas. I do not want you to claim them. I want you to understand what you're doing when you're playing with those formulas, trying to find t, trying to find v, trying to find s. I want you to understand what you're doing. So this is one method of finding the time of flight. Now let's look at another method. Now we've just looked at a way of finding the time of flight using the horizontal aspect of the motion. Now in this scenario though, I want to show you how to find the time of flight using the vertical aspect of the motion. It's important to be familiar with both of those two scenarios, because you do not know which variables you're given when it comes to facing the exam or you're given a certain problem set. You have to be familiar with both situations. Please do not claim either one of them. Be familiar with both. So in the previous scenario now, we relied on Vx, which was equal to V cos theta, which we said, and I'm going to repeat this, is constant throughout the entire journey from this point up to this point. But now, in the vertical aspect of the motion, where we are using Vy sine theta, this is the horizontal component of the velocity during the launch. This doesn't apply throughout the entire motion the way this applies throughout the entire motion. This doesn't apply throughout the entire motion. Please keep that in mind. The moment the particle gets to this point, the vertical component of the velocity has changed to something else. It's no longer this, it's something else. So this value of the component of the velocity only applies during the initial launch. Now, because the vertical motion is associated with acceleration, we have to pull our weapons associated with acceleration. And what is that? That is our formula. V is equal to U plus AT. Notice the acceleration. Whenever we're dealing with the acceleration, we pull the equations related to acceleration. And acceleration, I'll repeat guys, only comes into play the moment we start dealing with the vertical aspect of the motion, not the horizontal. In the case where we've got the horizontal aspect of the motion, we simply deal with the speed is equals to distance over time formula. Now, things have changed now. Let me rub this. We now have to deal with acceleration. Why? Because we're dealing with the vertical aspect of the motion. Which other equation do we have which has the variable of acceleration inside? We've got the equation v squared is equal to u squared plus 2as. And please drill, I cannot repeat this enough, drill these formulas inside your head. Know them inside of your sleep. Drill them, please. And our final formula, this is all you need by the way. Our final formula is S is equals to U T plus half A T squared. These are the only equations of motion we need when we're dealing with the vertical aspect of the motion. Please bear that in mind. Why do we need only these three? Or why do we need these three? Because of the variable of acceleration, which appears in all these equations. Why? Why do we need the variable of acceleration? Because it's involved in the vertical aspect of the motion of the projectile. Gravity, my brothers, gravity, my sisters, is what brings this into play. So later we're going to be substituting our values, which will, now please bear this in mind. I see a lot of people, a lot of videos, a lot of teachers saying for gravity, the acceleration due to gravity, when our object is moving downwards, you can use a negative value of the acceleration, say minus 9.81 meters per second squared. And when it's moving upwards, please use a positive value. They change the signs depending on whether the object is moving upwards during the motion or it's moving downwards. But as for you guys, you'll still get the correct answers. Please trust me. Do not change the sign depending on whether the object is moving up or down. Please use a single sign. If you're going to use a positive value, use that throughout. If you're going to use a negative value, use that throughout. I personally prefer a negative value. Why? Because the acceleration due to gravity is associated with downward movement. So just use one sign, guys. Do not interchange the sign depending on whether the object is moving up or down. Just use a single sign. You will get the correct answers. Granted, you use the correct signs for the velocity and the displacements. Trust me. Okay, so let's look at the time of flight in relation to the vertical aspect of the motion. Now, if you are asked to find the time of flight in this scenario, but you want to use the vertical aspect of the motion, there are multiple ways of attacking this. And I'll be showing them to you one by one, but I might leave some. But I'm going to be showing you definitely the most important. Now, the first way you can deal with this is to use this first equation over here. You want to find the time of flight. You can use this first equation. How do you use this first equation to find the time of flight? What is this? This is the final velocity associated with, in this case, the vertical motion. This is the initial velocity. This is the acceleration. And this is the time. Okay, let's make time the subject of the formula. Since we're looking for what? The time of flight. What would be time in this scenario? If we get u on the other side, we'll get v minus u. And if we divide by a, we would get v minus u all over a. So we'd get t is equal to v minus u all over a. Now again, ladies and gentlemen, please do not try to memorize this. This is simply this with t having been made the subject of the formula. Please do not memorize anything. That is the reason you learn the topic of subject of the formula in mathematics. So this is our time of flight formula in relation to the vertical aspect of the motion when we're using this first equation. But you have to be very, very careful when using this. This, like I'm saying, this is actually the time of flight formula for this entire journey when you're dealing with the vertical aspect of the motion. But please be very, 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 very careful when using this formula. Why? In this situation, if you want to use this equation as the time of flight formula associated with the vertical aspect of the motion, you have to really, really know what v is, what u is. You have to really, really know what v is and what u is. Failure to be able to deduce these two during the working of the question, then you will get the incorrect value of the time of flight. So in this case, I want you to really, really know what v is and what u is in this case. In this case, what is u? U is our initial velocity during the launch. So if we come here, that means we have v minus what is the initial velocity during the launch. The initial velocity during the launch is v sine theta. So we've got v minus, problem here. Okay, let's change this and call it v naught, so that it doesn't confuse us when we're playing with v, the sign. So this is v minus v naught sine theta all over t. Can you see this scenario? This is different from this. The reason reason I used V naught, I don't want anyone trying to factor out V, thinking that this is the same as this. This is our U, this is our initial velocity. And what is the final? Now, if you remember, this is a trick, if you will. If you remember from our first video, we said the final velocity here has the same magnitude for the points on the same level. So in this case, if our initial velocity has a magnitude of say 5, the final velocity has a magnitude of, again, of say 5. And then we also talked about the angles. Again, we said the angles are the same. So in this case, we would also have theta here for points on the same level if you watched the previous video. Now, what would be the vertical component of the velocity at this final point here? Now, let's call this V1. Let's call this V2. So this is V, okay, let's put a 1 here. So we don't confuse each other here. 1, 1. Now, so the vertical component associated with the motion at this point would then be V sine what? Sine theta. Sorry, V2 sine theta. This is the vertical component of the velocity at this point, which is at the same level with this point. So if we substitute it here, what do we get? We get T is equal to what? Okay, let's put it this side. T is equal to what? T is equal to V2 sine theta minus V1 sine theta all over A. Look at this. All over A. Now, in this scenario, this is the same as this. Why? Because we talked about this in the first video. The magnitudes are the same. But do not memorize this. This is just a special case for this scenario. If our object ended at this point, we would have a different value for this completely. So don't memorize this. In real time, you would have to compute the values for this. So please do not memorize these formulas. All you have to know in order to arrive to all this is you just have to know this single formula. And you have to work your way through understanding. What are you looking for? I'm looking for the time of flight. And then you make T the subject of the formula. And then you start looking for the values of V and U. How do you find them? That's when you begin resolving or finding these funny looking formulas. And then you compute the values. Your value of A will be already given. Most likely you will know what it is. It's usually 9.81. That is the acceleration due to gravity. Some might prefer that you use 10. It depends on the scenario. Use whatever they provide you with. So this is the way you find the time of flight associated with the vertical component or the vertical aspect of the motion using this simple equation. But please, I repeat, know what the final velocity is and know what the initial velocity is. Now I'm going to show you another way which I prefer. This is the method I prefer, though this is fast. This is the method I prefer. Using the same formula, by the way. What is the method? The method is this. We break the motion into two aspects. And then we say T is associated with the movement from point A up to the point where the final velocity is 0. Remember, when we are at the peak during the motion of the projectile, when we are at the peak, the final velocity or the velocity at the peak here is 0. Not just the velocity in general, as in the raw velocity. No, the vertical aspect of the velocity, the vertical component is 0. In general, the velocity is not 0 at this point, but the vertical is always 0. And since we're dealing with the vertical motion in this case, we can say, let's say, from this, moving from point A to this point, it takes t1 seconds. And then moving from this point up to this point B, it takes t2 seconds. So what do? We say, okay, t1. How do we get t1? Remember, I say the final velocity moving from this point up to this point, the final velocity, the vertical component of the velocity is 0. So we end up with something like this, minus u over a. So that is t1. So what is this? This is half the time of flight, because we're only looking at half the motion. And then we have to find t2. How do we get t2? Again, we use the same formula. We use the same formula. But in this case, since we have a vertical component of 0, in this case it served as the final velocity. But in this case now it's serving as our initial velocity for what? For moving from this point to this final point B. So as our initial velocity, we'll make it 0 here. So what do we end up with? T2 is equal to V, what is left? All over A. So this is our formula for T2. So this is the other half of the time of flight. How then do we get the time of flight? We say T1 plus T2. Let's do that. T1 plus T2. What do we get? We get minus U all over A plus V over A. And if we bring this side, what do we get? We get V over A minus U over A. Common denominator, guys. V minus U all over A is our what? Remember, we said this is then the time of flight. Is our time of flight. So see something. We come back to this formula. What I mentioned initially, that you can use this formula as the formula for the time of flight in general during the whole aspect of the motion. But if you're considering the vertical aspect. So this is the same as this. But this is a safer way, in my opinion, of calculating the time of flight. That is by breaking it into two pieces. The first piece, you deal with the first piece first, and you deal with the second piece first. Another way, if you can see another way, maybe this is method 3. You calculate the first piece of the motion and bear in mind that this is equal to this in value. So you do not need to calculate T2. All you have to do is, when you find this value, you multiply it by 2. Once you multiply it by 2, you get the total time of flight, or the time of flight. But you might be worried and be like, is that okay? Since we've got a negative, we're going to get a negative time. No, we're not going to get a negative time. How do we do that? During our initial velocity, our object is moving up, so it has a positive value of the velocity. And then our acceleration due to gravity, like I said, I prefer to use the negative. Using the negative forces me to use the positive for the initial velocity when the object is moving up. So we've got a negative here and another negative due to the direction of the acceleration due to gravity. Divide those negatives, and you get a positive. On the other hand, if you prefer to use a positive value for the acceleration due to gravity, naturally, because you have inverted the Cartesian coordinate system, you are going to have to use the negative and negative for the initial velocity, that is the vertical component. You're going to have to use a negative when the object is going up. Why? Because you have inverted the Cartesian coordinate system. So you won't get a negative value for time. If you're getting a negative value for time, you're probably messing around with the signs. So this is our way of finding the time of flight using what? Using this simple equation. Now, if you look at the second equation, we do not have any variable associated with t. The only equation associated with t is this third equation. So I'm not going to look at this equation. It's essential for other elements of projectile motion, but not when we're calculating the time of flight in this particular scenarios. We can use it, yes, in some ways, through substituting and so forth, but in this scenario, we're just going to look at this equation as it is in its raw form. So let's do that. So this is our second equation of motion, which is associated with the variable t. Again, put it in your mind, we're dealing with the time of flight. So the reason we picked this equation is simply because it has this, the variables t. Now, how do you find the time of flight using this formula? It can be a bit tricky if you're not familiar with, very familiar with the idea of displacement. But in this particular case, I'll tell you, in this particular case, where our object is launched from point A and arrives at point B, and point A and point B are at the same level, this S is the displacement. So, not just the displacement, in this particular case, is the vertical displacement. In this particular case, is the vertical displacement. So notice something. Our object during this motion goes up. When it goes up, it acquires a certain displacement. How do you find the displacement? It's simply the final position minus the initial position. So if we assign, say, this first position at 0, and we want to find the displacement, say we'll get a displacement of, say, positive m. Say we're using the Cartesian coordinate system in its normal orientation. And how do you find the displacement from this point up to this point? That is for this aspect of the motion. We say final position minus the initial, but the final position in this case is 0, and the initial is associated with that. So we end up adding this. How do we get this? It's simply 0 minus m. So it gives us minus m. This is the second aspect of the displacement. Please do not pay close attention to this. I just want to justify what I'm about to do when playing with this formula. So if we add this, we'll notice that we get a displacement of 0. We get a displacement of 0. Now I'm going to rub this. So if you do decide to use this formula, I do not recommend using this formula. But when things are tight in your test, in the exam, and you're forced to use this formula, please bear this in mind. So the displacement during this entire journey we have just shown is 0. So S is 0 during this entire journey. So it leaves us with this. S is equal, 0 is equal to U T plus half A T squared. Now, if you look closely, what we have in this scenario is more of this. Half A T squared plus U T plus 0 is equal to 0. Now, why do I say plus 0? The reason I say plus 0 is because I want you to invoke this into your mind, that this is simply a quadratic expression. So the way you get the value of t in this scenario, where you decide to use this funny looking formula, you end up with a situation where you have to solve for t using the quadratic formula. Most likely using the quadratic formula. I can most likely guarantee you that most of the time, these values won't be so friendly. So you are going to be forced to use the quadratic formula. So what is the quadratic formula? If I remember correctly, in this scenario, t is equals to minus b plus or minus b squared minus 4ac all over 2a. Yes. All over 2a. So what is your a in this scenario? Your a would be half the acceleration. Now this a and this a are not the same, please. This is the acceleration. This stands for this first part of the expression. Then your b, what should be your b? Your b would be this part of the expression, which is the initial velocity. And what would be your c? Our c is 0. So automatically, this is put out of the question. This is put out of the picture. So you're just left with b squared. This is how you're supposed to tackle it when you decide to use the formula s is equals to ut plus half at squared. This is how you get the time of flight. Again, you still have to pay attention to the signs here, things like the signs. You have to pay attention. In this case, if you decide to use a negative value for the acceleration due to gravity, use a positive value for the initial since it's going up. So you have to pay close attention to that. And remember, the 0 comes from the fact that going up and down is just equivalent to 0 displacement. So yes, this is the equation you use if you do not want to use this simple looking formula. I'm sure you can see this, guys. This doesn't look very, very welcoming. So I prefer that you use this whenever the situation allows. Now, let's look at how you get the time of flight for other parts or trajectories that are not necessarily this nice. Now, this is the final example we're going to be looking at. What you're going to learn from this funny looking example can be applied to all forms of the motion, all forms of trajectories you can find. So, pay close attention. Now, in this particular scenario, if you are asked to find the time of flight, let me put this V. If you are asked to find the time of flight, the best way I recommend, you still have to deal with the formulas. V equals equal to U plus AT, and S is equal to UT plus half AT squared. You still have to use these formulas, either of the two or both of them, depending on the scenario. Now, in the first case, this works like magic. This works like magic, as long as you know how to compute the displacement in this particular scenario. If you know how to compute the displacement, say the displacement for this entire journey is, say, F. Or let me use a different color. Say the displacement for this entire journey is F. You have to equate it to the rest of the expression, ut plus half a. And again, you'd have to turn this into the quadratic expression. And how do you do that? You simply get f on the other side of the equation, leaving you with this, half a t squared plus ut plus minus f So you'd have to find the value of t. Finding the value of t would then give you the time of flight for this entire motion. It just applies like in the previous scenario. The difference being that in this case c is not 0. C is the displacement associated with this motion. Now, we're going to be looking at a couple of examples later in time, but for now, we just want to drill in the understanding of the ideas. Now, so this applies for the formula S is equal to ut plus alpha at squared. Now, for the scenario where you want to use v is equal to u plus at, first we make t the subject of the formula. You already know what that is. You get something like this. For this scenario, again, just like in the portion I mentioned when describing this scenario, for this case you break it up into two. You break the motion into two parts. The first part being the part where our object moves with its initial velocity and reaches a point where it has a final velocity, a final vertical velocity of 0. And then the second part being the motion where the initial vertical velocity is 0 and the final velocity is whatever it is. That is whatever you find for the vertical velocity. Now, in this case, the vertical velocity, the final velocity won't be in any way similar to this initial velocity. Why? Because of the different levels. So do not try to memorize like I mentioned. So in this first case, what you'd get is, let's call this again, let's call it V1. So in this case, how do you get T1? T1 is equals to, what is the final? The final is 0, since the first aspect of the motion is only associated with ending at this point. So in the first part, the final velocity is 0, giving us this formula. So using this little formula, this is how you compute the value of T1. That is the first portion of the motion. Then for T2, since our initial is now 0, this means we get V over A. Notice, I want you to notice that this is exactly the same thing as we had in the beginning. But unlike in the beginning now, this won't be similar to this. Why? Because this and this are completely different. That is, the velocities at this point and the velocities at this point are completely different. Now, u in this case, this u, in this case, u would be what? U would be V1 sine theta. If you want to compute the first portion of the motion, the time associated with the first portion of the motion, then A would simply be the acceleration due to gravity. Now, in this final scenario, in this final scenario, you have your velocity of V2 associated with a certain angle which has nothing to do with this because these are not at the same level. Let's call this angle alpha. So in this scenario, the vertical component of the velocity, which will be our final in this case, is V2 sine alpha. So this V is equals to, let's call it, this is V2, so it's equal to V2 sine alpha, not theta, alpha. So that's why I said whatever the velocity is, because it's not the same as this, like in the first case I mentioned, or in the first case we looked at. So this is how you'd compute the time of flight in this scenario. You then add T1 to T2, getting a total of T1 plus T2 is equal to what? It's equal to minus V1 sine theta all over A plus V2 sine alpha all over A, which is equal to V2 sine alpha minus V1 sine theta all over A. But in this scenario, these are not the same as in the first scenario. In the first scenario, these were of the same magnitudes. In this scenario, V2 is completely different, V1 is completely different. Why? Because these points are at different levels. They are at different heights. The same applies for these. These angles are completely different. Why? Different heights. So you'd have to compute and find out exactly what theta is or what alpha is, depending on which of the two you're given and which of the two you're not given. So this is how you compute the time of flight using our usual simple formula over here. And if you are given the opposite case, say the object is projected from this point and it lands at this point, again you would have to divide the motion into T1 and T2 and do the necessary math, which remains the same. It's always this simple. The math doesn't change. It's always this simple. You would have T1 is equals to minus U all over A, and for T2 you'd have V over A. But you would have to find out what exactly is the value for U and what exactly is the value for V. This is how you compute the time of flight, and this applies for any question you're given related to time of flight. This is the method. That's how you calculate the values of the time of flight. Master these and you'll be able to tackle any question related to time of flight. Now, like I mentioned, later in our videos, I'll be looking at examples associated with all the topics we are looking at. Examples associated with the time of flight, examples associated with the range, examples associated with velocity, examples associated with peak height. We're going to be looking at examples actually using numerical values, substituting things and getting numerical values back so that you get a feel of how all this works. Thank you guys for watching this video. Please leave a like, subscribe and a comment if you enjoyed it. See you in the next one. Thank you.